Well, one of the things that we often hear when we talk about CMOS technology is the are numbers like 180 nanometer or 90 nanometer or 45 nanometer. That refers to technology node, right? Another name that we use for is technology node, and that's a very important part of CMOS technology. We know that it has been continuously evolving for the last almost 50 years. And there was a time when we said something like 1 micron technology. It meant that the minimum channel length, minimum gate length that we can have is 1 micron. Or when we said the technology is half a micron, what was meant was that the minimum gate length was usually the gate length is the minimum dimension that is there in a technology. So that was half a micron. So let's look at some of these technologies and see what these numbers really mean. For example, when we say 180 nanometer technology, and what does it really imply? So what we have shown here is, in this particular case, a two MOSFETs here, two N-channel MOSFET here. So these are the source drain diffusions here. Two N-channel MOSFETs fabricated side by side, and you can see in the red color is the polysilicon, and then in blue color are the and so if we look at so we are talking about 180 nanometer technology. So we look at the actual gate length LG, the physical gate length that is there here. So that is 130 nanometer. All right, so that's not 180 nanometer, but that's 130 nanometer. And there are a couple of other interesting dimensions here. Note that there is something called gate to contact spacing here, right? So this is the edge of the gate here, and this is the source drain contact here. And the difference between the two is what we call as the gate to contact edge here. So that's 160 nanometer. So that's close to 180 nanometer. And one of the very important dimensions is what we call as the contacted gate pitch. Contacted gate pitch. So this tells us how close can two, let's say, NMOS transistors be. So it's basically from the center of the gate here and the center of the other gate here, and the difference between the two, right? So contacted gate pitch is 636 nanometer here. And of course we can break contacted gate pitch, L pitch. It would be made up of the gate length, and then the gate to contact length, and the contact WC is the contact length that is there here. So that comes out to be 636 nanometer here. So note that the first thing that you note here is that the gate length is not, minimum gate length that we can have is not 180 nanometer, but it is 130 nanometer. And the other important point is the contacted gate pitch. Basically the separation between one gate and the other NMOS gate. So that gives us the contacted gate pitch, which is 636 nanometer here. All right. So these are some of the dimensions that are there with 180 nanometer. Now let's go to 90 nanometer technology here. So let's look at these numbers from 90 nanometer technology here. So when we go to 90 nanometer technology, note that the gate length, even though we are calling it 90 nanometer technology, the gate length is only 45 nanometer. It's almost half of that here. 45 nanometer. So and there are other and the contacted gate pitch. Contacted gate pitch is 310 nanometer here. And this LGC here, gate to contact, right? So the edge of the gate contact and the edge of the source drain contact here. So that is about close to 90. This is close to 87 nanometer here, right? Close to 90 nanometer here, LGC here. And spacer layer is the the separation between the gate edge and the source drain edge here that you see here. So that's the spacer layer that is there here. The point again is that the gate length is not 90 nanometer, but it is the physical gate length is 45 nanometer. And the other point is the contacted gate pitch is 310 nanometer. Now, if we compare the difference between the two, so as we went from 180 to 90 nanometer, look at the change in the gate length. The gate length went from 130 to 45, so a factor of 2.88. Right, so the change in the gate length, the physical gate length, is not the same as as we go from 180 to 90 nanometer, a factor of 2. On the other hand, the contacted gate pitch, right, the contacted gate pitch, earlier it was 636 nanometer, now it is 310 nanometer, and that's a factor of 2. So when we went from 180 nanometer to 90 nanometer technology, we are seeing a factor of 2 difference. So where the factor of 2 difference comes in is the contacted gate pitch, and not the gate physical gate length here, right? And let's look at some of the other technologies which are there here, so we can see how the technologies have evolved. So for example, so for 250, this is 250 nanometer, the contacted gate pitch is 910. The physical gate length was 180, and there are other things. 130 is the spacer thickness, and gate to contact spacing is 240. All right, so one can clearly see that the physical gate length is of course related, but is not the same as the name of the technology node here. So when we have 180 nanometer, the gate length, physical gate length is 130. When we have 130 nanometer, the physical gate length is 65. Similarly, as you go to, let's say, when you go to 65 nanometer technology, the physical gate length is only 35. When you go to 45 nanometer, the physical gate length is 30. Right? And the other thing is, what we can clearly see is the contacted gate pitch. That's a very important parameter. This is the parameter which would determine how dense, how many transistors you can put in a certain area here. So the contacted gate pitch is a very crucial parameter here, and that scales as the technology node number. Here you can see, for example, we've already seen that when you go from 180 nanometer to, let's say, 90 nanometer, 180 nanometer to 90 nanometer, we go from 636 to 310. So we can clearly see that as you go from 180 to 90, the contacted gate pitch becomes half here. Similarly, as you go from 90 to 45, so 90 to 45, at 90, contacted gate pitch is 310, and at 45 is 155 here. So again, you can see a factor of 2 here. All right, so the point was that earlier in the beginning, when we said it's a 1 micron technology, it often meant that the physical gate length was very close to that. But now you can see here, physical gate length is significantly different from technology node number here. As an example, when we have 90 nanometer technology, the physical gate length is only 45 nanometer here. And the other point to remember is that one of the important parameters that determines the density of circuits, density of transistors, number of transistors per millimeter square and things like that, depends on a very important parameter called contacted gate pitch, which is the separation between the center of one gate, one NMOS gate, let's say, and the other NMOS gate here, right? So that's the contacted gate pitch. And that depends on several factors that you can see here. It depends on the spacer thickness here, depends on an important parameter called gate to contact, the separation, minimum separation between the gate edge and the contact, source drain contact edge here, then the minimum thickness of the contact itself. So it depends on all of those parameters that are there, and determines how close you can bring one NMOS. This is one NMOS transistor, NMOS 1, and this is the other NMOS transistor, NMOS 2 here, and how close we can bring them together, right? So that determines the density of the circuits that is there here, and that's determined by the parameter called contacted gate pitch here. And that is the parameter that scales when we go from 180 to 90, and we see a scaling by a factor of 2. So what is really getting scaled is the contacted gate pitch here. And so these are, of course, for planar transistors. Present day transistors are quite different. FinFETs, for example, and maybe in a separate discussion, we'll see what those numbers, 7 nanometer or 10 nanometer, what those numbers really imply here. All right.